Light intensity and quality. This presentation was developed by Dr. Margaret McMahon and Miles Jonard from the Ohio State University, Dr. Thierry Kubota from the University of Arizona, Dr. A.J. Both from Rutgers University. This presentation includes several key information. The first one is regarding what is light. And we are talking a little bit about the light and its physical properties. Secondly, we are going to talk about how to measure light, important for controlled environment agriculture. Third, how does light interact with plants? Some basic plant physiology, horticulture science. Number 4, different supplemental lighting sources. Light qualities are very different for different light sources. And then finally, we talk about applications, how to increase and decrease light under controlled environment agriculture setting. So what is light? Human eyes detect light, and that specific light is called visible light, the light we can actually see. And light is generally electromagnetic radiation, and visible light is within the waveband of 380 to 770 nanometers. Plants also respond to light and in a slightly different waveband. The waveband plants can respond is from 300 to 800 nanometers. And specifically, plant photosynthesis responds to the waveband of 400 to 700 nanometers. And this waveband is defined, therefore, as photosynthetically active radiation. You may have heard of PAR, which actually stands for photosynthetically active radiation. So the diagram below is showing the wave bands and then also name of the electromagnetic radiation. And then you can see that visible light is sandwiched between ultraviolet radiation and infrared radiation. So those are also electromagnetic radiation. But again, visible light starting from 380 to 770. Starting with very dark purple, going into blue, going into green, yellow, orange, red, and dark red, and finally you can't see. So that's the visible radiation or light. So the photosynthetically active radiation, as I said earlier, 400 to 700 nanometer. This diagram or chart is showing actual plant photosynthetic response measured as quantum efficiency. So it's a relative efficiency compared to the peak efficiency happening in orange-red range. And then as you can see, the high efficiencies occurring between 400 to 700 nanometers. Plants have different pigments other than chlorophyll, which is governing photosynthesis. And phytochrome is another plant pigment, changing its form based on the light quality. And it's very unique response and specifically responding to red and far red light. And red is the light between 600 to 700 nanometers. And far red is generally considered as 700, 800. And then depending on the original light quality or incident light quality, the amount of far red absorbing form and red absorbing form is determined. and that resulting ratio of far red absorbing form and red absorbing form determines the response, such as germination and flowering. So this is another diagram showing phytochrome system. This is a red absorbing form that absorb red light and turn into far red absorbing form. And far red absorbing form absorb far red light and then change the form to the red absorbing form. Far red absorbing form also degrades in darkness, and this is the form is very active in the plant system. So from here we are going to talk a little bit about measuring light quality and measuring light intensity or irradiance. So the light is considered either as a particle or a wave. And this light particle is called a photon. And each photon has its wavelength specific energy level. And that energy level can be computed using this equation, showing the characteristic of its energy inversely proportional to its wavelengths. So that's why wavelengths is in the denominator to express the energy level per photon. To measure or quantify spectral distribution, the instrumentation we need to use is called spectroradiometer, and that is looking like this unit shown in this picture. And then the reading of this kind of equipment may be like this chart. And this is showing two kinds of reading from the same light source. One is shown in a photon flux base. The other one is energy base. Because energy level per photon is different and determined by different wavelengths, that's why the shape of the scan is different when it is shown in energy base or photon base. So the photon base data basically is showing number of photons quantified using a unit mole received per surface area square meter per second, and number of photons of each wavelength per nanometer base shown in this green chart. And then energy based distribution of each nanometer or wavelength is shown in this red chart. So the unit of photon flux based reading from spectroradiometer is micromoles per square meter per second per nanometer. And energy based reading is watt per square meter per nanometer. And if you integrate the value between 400 and 700, every single nanometer reading of photons, micromoles per square meter per second, and integrate the value every single nanometer, basically sum up, then you can get per micromoles per square meter per second, 400 to 700 nanometer. If you look at different range, for example 700 to 800, and then you sum up all the readings in micromoles per square meter per second per nanometer, if you sum up for the range of 700 to 800, then you get photon flux of that range, in this case far red range, 700 and 800. So that's how you use spectroradiometer. You can get ratio of specific light qualities such as red and far red, or you can get something different, blue and red or blue and green ratio if you have this instrumentation. It's very useful instrumentation to work on light quality environment. Much simpler equipment is available for measuring PAR. So the PAR is always 400 to 700 nanometers according to the scientific definition. And then the instrumentation, like in this picture, can integrate the reading within this prefixed range, 400 to 700 nanometers. So it measures the instantaneous light intensity, and it measures the number of micromoles of photons striking a surface area of 1 square meter over a time period of 1 second. So it's an instantaneous measurement. And the readings are sometimes called photosynthetic photon flux and abbreviated as ppf. So the ppf is the unit of measurement, PAR. So just a little bit about the unit micromole. Mole is the unit to quantify the amount of particles. And 1 mole of light particles equals to Avogadro's numbers of photons. So you can actually find number of photons by knowing how many moles. So 1 mole equals 6.022 times 10 to the power of 23rd photons, so many photons. And that is actually 1 million micromole. Micro is prefix to show 1 over 1 million. Therefore, if you express 1 mole using micromole as unit, it is 1 million micromole. Therefore, 1 micromole actually means 6.022 times 10 to the power of 17th photons. And this understanding is very important when you need to convert a photon-based unit to energy-based unit using the equation previous shown, how much energy is contained per photon at that given wavelength. Another important parameter used widely in horticulture and horticulture engineering is DLI, which is daily light integral. So as you learned in the previous slide, PAR is a measurement instantaneous, and DLI is more cumulative value. So it's like a rain gauge and often expressed per day. So integrated photons, amount of photons in that range, 400 to 700 per square meter base per unit of time, and often it's a day, 24 hours. And then usually nighttime there's none, so it's basically daytime integration. The solar radiation includes not only PAR but also other wavebands, and a much wider waveband, 280 to 2800 nanometers. And therefore, often in horticulture engineering, you need to quantify the amount of solar radiation, not just PAR, because solar radiation contributes a lot to the heat accumulation inside the greenhouse. And then we use a sensor called pyranometer, and that is designed to measure solar radiation. Because of the fact that much of the energy turned into heat, therefore the unit used for solar radiation is often watt per square meter. And also, we use daily integrated solar radiation. In that case, the unit turns into megajoule per square meter per day. Some people use joule per square centimeter per day, but in terms of scientific notation, use of per square meter base is better than per centimeter, per square centimeter base. So you need to pay attention which unit is used, otherwise the magnitude of value is very different, per square meter base or per centimeter base. So how does light interact with plants? The most important process is photosynthesis. It allows plants to grow and develop. And that is a reaction converts water, CO2, using light energy into sugars and oxygen. And this is a chemical reaction shown, simple way, the photosynthesis. And the reaction is very temperature dependent, particularly the carbon reaction. And if you want to understand further regarding the reaction, most of the plant physiology textbooks include the details of this reaction. In addition to photosynthesis, light has also a thermal effect. Therefore, it is a heating source for plants. In fact, sunlight contains a lot of thermal radiation. And also, most of the power absorbed by plants is eventually converted to heat because plant photosynthesis is not efficient process, and that's why most, if not all, PAR absorbed by plants also considered as a heat source for the plants. And then also light has signal to the plants to let plants know when to bloom. For example, some plants are sensitive to the day length or dark period length, and the seasonal changes of this length can signal the onset of flowering. Another influence of light is through photomorphogenesis. Photomorphogenesis is a process affecting plant morphology, and germination is a good example in response to light, and the quality of the light plays a significant role in the germination control as well as other photomorphogenesis. This is a solar radiation spectral signature expressed or measured in the unit of watt per square meter per nanometer. And here is the PAR range, 400 to 700 nanometer. And the rest is infrared radiation and UV radiation. And the range, total range of solar radiation is 280 to 2800 nanometers. So let's talk about applications. We learned that light is important in photosynthesis and other plant responses. And then we learned that how to quantify the light in terms of intensity or radiance, and then also light quality. So increasing light in a plant growing system can be done by supplemental lighting. And high pressure sodium is one of the widely used light source in the greenhouse. It has a very unique spectral signature. So again, 400 to 700 is the PAR range. And you can see high pressure sodium lamp is emitting a lot of yellow orange radiation, and not much in blue, not much in the dark red range. And high pressure sodium lamp is a very high power lamp, so the input power ranges from 400 to 1000 watt. And in greenhouse, having high power lamp is very important so that number of fixtures can be reduced rather than putting so many fixtures overhead in the greenhouse. So this is high pressure sodium installed in Rhodes production greenhouse in the Netherlands. You can see that still, high density, high pressure sodium. But again, if this was much lower power, then the density could have been a lot higher. Another common light source may be metal halide lamp, and very different spectral characteristics compared to high pressure sodium. It has more blue component and then also even UV 300, 400. And then again, that's red, and then very little far red. And then this is a research facility having a combination of yellowish high pressure sodium and then whitish metal halide lamps. And combination of high pressure sodium and metal halide lamps is very common because those two light qualities can be complementing each other. One is lacking blue, the other one is very rich in blue. Fluorescent lamps may not be so common in greenhouse production system, but it is still widely used for germination area and then also indoor nursery area. Therefore, I would like to show you in here. It's a wide spectrum, including a lot of blue, a lot of green, and a lot of red. And this is one of the example pictures used in a research facility, artificial lighting based facility. So bank of fluorescent lamps installed overhead and to grow the experimental plants underneath. Typical setting. Another widely used light source in greenhouse plant production is incandescent lamp. So incandescent lamp, because of the low efficiency of energy, it may not continue for long time anymore, but it has been used widely for photoperiodic control. Because the light quality is very rich in far red, very important light quality for phytochrome response. Therefore, incandescent light or incandescent lamps have been considered very unique and important light quality for photoperiodic control. However, because of the energy inefficiency, we are actually in need to develop something to replace incandescent lamps, and some companies already developed replacement lamps based on light emitting diodes, LEDs. And this is incandescent lamps installed in a floriculture greenhouse, of course, for flowering control. So, speaking about light emitting diodes, LEDs are relatively new light source, and uniqueness of the LEDs include the monochromatic light characteristics. Therefore, you can combine different colors and design spectrum for different crops. However, because of the flexibility, lots of potentials for application in horticulture, and currently many research programs are going to optimize the use of LEDs for horticultural application. And this picture is showing use of red and blue LEDs over seedlings. Red light is selected because of its high efficiency to drive photosynthesis, and blue light is selected because of the need for maintaining morphology of the plants. And this is application in greenhouse as a supplemental lighting. This is actually intra-canopy lighting or interlighting, and that is designed to provide photons for lower canopy, which usually dark side of the canopy compared to top of the canopy. Right, let's talk about the way to decrease light, shading. Why do you need to decrease light? Light is very important for photosynthesis. Therefore, you want to maximize light intensity in a greenhouse. However, too much light can be damaging to plants. And then also during the summertime, you got to reduce sunlight because sunlight includes a lot of heat, and even PAR eventually becomes heat to the plants. Therefore, if the system doesn't have high enough cooling capacity, you got to reduce sunlight. And in most cases, you use shading. And putting shade cloths either internally or externally of the greenhouse system is the easiest way to decrease the overall light intensity. And there are multiple shading percentages available for shade cloth used for greenhouse controlled environment. Generally, the weave of shade fabric will determine the amount of light allowed to penetrate, and shade curtains are available in different design, resulting in a range of shade factors. And then also some shade curtains have different colors and can filter out certain part of light spectrum. So you can do a lot using selecting shade curtains. And then also some shade curtains can be considered to have another function, which is very important for energy saving. And this is an example of internal shade curtain, automatically controlled based on the light intensity and temperature inside the greenhouse. This is another shade curtain, which is probably a lot higher shade percentage compared to the previous one. Thank you very much for listening.